Welcome back to Mathematics Lifeline. In today's video, I want to talk about the ratio test and how it is so useful in testing for convergence of infinite series. Let's first talk about the actual rule of the ratio test. So if we're given an infinite sequence of real numbers, a sub n, we're going to consider this limit. So the limit is n goes to infinity of the absolute value a sub n plus 1 over a sub n. So whatever we get for that limit, if that value is less than 1, then the series of a sub n will converge. So this is usually from n equals 1 to infinity. If L is greater than 1, so that limit is greater than 1, that means that the series will diverge, and if it's equal to 1, then the test is inconclusive. So when you first see this, you may think of it as kind of a general rule, you just have to memorize it. But there is logic behind this if you think about the theory. What we're comparing here is we're comparing the next term with the previous term, right? So when we have, like, we're looking at a term of a series, we're comparing the next term with the one right before it. And we're looking at the size of that ratio. So visually, you can kind of see it here. If we look at these ratios and every term is smaller, like the height of all of these rectangles is smaller than the previous, then that series will converge when we add those, because eventually this will get so small that it adds nothing to the series, right? It adds practically nothing. It's infinitely small. But on the other hand, if I start here at a really small value and every rectangle is bigger than the one before it, then it would make sense that that series would diverge, right? It would add up to some infinite value because these keep getting infinitely bigger as we go off to infinity. And so you're just adding infinitely big numbers, and that's never going to converge. So using this logic, let's look at a few examples to try to use this ratio test practically. So the first series we want to test for convergence is the sum from n equals 1 to infinity of 1 over n factorial. So the ratio test is very helpful for these factorials. When we have factorials in a series, your mind should almost immediately go to ratio test because it's so helpful here. So let's look at the limit. So we need to look at the limit as n goes to infinity. We need the absolute value of a sub n plus 1 over a sub n. So first, let's identify what a sub n is. A sub n is the argument of the series here. So when we look at this, our a sub n in this case should be 1 over n factorial. Right, so now let's think about what a sub n plus 1 would be. So a sub n plus 1 is just going to be plugging in n plus 1 where we see an n. So it's 1 over n plus 1 factorial, right? So those are the terms that we need here. So let's go ahead and write those in this limit. So the limit as n goes to infinity, we have 1 over n plus 1 factorial over 1 over n factorial. Right, this is the limit that we're looking at. This is directly from, this is L. It's going to give us L. This is directly from the ratio test because I'm plugging in n plus 1 here and just a sub n right there. So we can go ahead, and since we're dividing fractions, we can flip and multiply those fractions. So this is the same thing as the limit as n goes to infinity. So we have the absolute value. Now, if I flip and multiply, I'm going to get the n factorial is going to come up to the top, and we'll have n plus 1 factorial on the bottom, because those ones don't affect anything. So I just have n factorial over n plus 1 factorial. So this looks a lot neater now, but we still can actually simplify this a little bit more and make it really easy to evaluate this limit. So let's consider what n plus 1 factorial is, right? N plus 1 factorial. What is that equal to? Well, it's equal to the first term. So we basically just subtract 1 and multiply all those terms. Like, for example, 4 factorial is 4 times 3 times 2 times 1, right? So we keep going like that forever, but with n plus 1. So when we write that out, n plus 1 factorial is going to be n plus 1 times n times n minus 1 times n minus 2, right? So we need to kind of look at what we have here. This is an n plus 1 term, but the rest of this is actually going to be the same, and it keeps going on, is going to be the same as n factorial, right? Because n factorial is equal to n times n minus 1 times n minus 2. Sorry, write that a little bit better. Times n minus 2 times dot dot dot. Right, so this is n factorial. We have that right here. So that means that whenever I want to rewrite this limit, I'll have the limit as n goes to infinity of, instead of the denominator being n plus 1 factorial, I'm going to write it as n plus 1 times n factorial. And now you can probably see what happens here. Those n factorials can cancel each other out, right? So I get the limit as n goes to infinity of the absolute value of 1 over n plus 1. And now this limit is super easy. We can basically just plug in infinity because the denominator gets really, really small, or really, really big, so the fraction gets really, really small. So as n goes off to infinity, this limit will be 0. And that's equal to the L that we talked about right here. So we have that L equals 0. So L is less than 1. Right? If it's 0, it has to be less than 1. So the series will converge. So n equals 1 to infinity. 1 over n factorial converges. And that's it. So this one was a pretty standard starting example for the ratio test. Factorials are really, really easy to solve with the ratio test because of this cancellation that we usually get. When we have something like this, you always will want to try to cancel some of those factorials because we still don't want to do a limit with a factorial in it. So you want to try to get rid of any factorial term that you have. And it's nice because they usually will cancel like this, and you can evaluate this limit super nicely. So yeah, we found that the sum from n equals 1 to infinity of 1 over n factorial does converge, and this was by the ratio test. So let's go ahead and look at another example. All right, so let's look at this example. We're going to look at the sum from n equals 1 to infinity of n factorial over 3 to the power of n. So again, we have that factorial term, and exponential terms are another one that are really easy to use the ratio test on. So like for your convergence of geometric series, you could test that using the ratio test. Of course, geometric is probably going to be easier to see because it pops out much faster, but it's perfectly valid to use the ratio test on those types of questions. But let's go ahead and figure out what our a sub n is. So our a sub n is the argument of the function, which is going to be, or the series, n factorial over 3 to the n. So when we look at a sub n plus 1, that's going to be n plus 1 factorial over 3 to the n plus 1. Right, so those are the terms that we need for our limit. So we're going to go ahead and set that up. So we have the limit as n goes to infinity. The absolute value, so the first thing is a sub n plus 1. So that's n plus 1 factorial over 3 to the n. And then we divide that by the original a sub n. So that's n factorial over, or sorry, this should be n plus 1 over 3 to the n. Right, so that's our a sub n plus 1 over a sub n. So again, we have this nested fraction, right? So what we're going to want to do is flip and multiply. So this is going to be the limit as n goes to infinity, the absolute value. So when I do this, I'm going to end up getting an n factorial in the denominator and a 3 to the n in the top. So I have n plus 1 factorial times 3 to the n all over n factorial times 3 to the n plus 1. All right, so this is just dividing by that fraction, so we flip and multiply. So that's what we have now. So what we want to do is try to figure out some things that cancel. So in exactly the same way that we talked about before, n plus 1 factorial breaks down to that n plus 1 times n factorial. So let's go ahead and write that. So we have the limit as n goes to infinity. So the numerator we're going to break down to n plus 1 times n factorial. So then we still have this times 3 to the n. Now we also want to try to cancel that as well. But the nice thing is we can cancel it down here, right? So we still have n factorial. But then right here, 3 to the n plus 1 is the same thing as 3 to the n multiplied by 3. Right? This is always true because remember, whenever we are multiplying things that have exponents, we're actually adding the exponents. So this is technically a 3 to the first, but since we're multiplying these two, we get 3 to the power of n plus 1, right? Because we add those exponents. So this is the same way that you can break that down, very similar to how we break down the factorial. But now look at all the stuff that cancels. N factorial and n factorial cancels, 3 to the n and 3 to the n cancel. So then we end up with just the limit as n goes to infinity of the absolute value of n plus 1 over 3. Right, so when we look at this, it's pretty clear to tell that this will actually go to infinity. Right, when I put infinity in here, I get infinity over 3, but that's still infinity. And the absolute value doesn't affect anything since everything in here is going to be positive anyway. So it affects nothing. We know that L is equal to infinity, but infinity, of course, would be greater than 1, right? So this is greater than 1. So that tells me that the sum from n equals 1 to infinity of n factorial over 3 to the n will diverges. So it will diverge, sorry, not will diverges. So it will diverge. I guess I should write diverges here. But yeah, so this is another example of where the ratio test can be helpful. So your exponential type functions are pretty useful. And again, like I said, you can use the geometric series if you don't have the factorial, right? So just any exponential you can test with ratio test as well. So pretty simple, pretty smooth process right there. Again, the whole thing is just identifying your a sub n plus 1 and your a sub n. And then from that, it's just algebra to get the rest of it. And then you have to take the limit at the end. But yeah, so we got that the L goes to infinity, right? That's greater than 1, so the series diverges. All right, let's go ahead and look at one more example. All right, so let's go ahead and look at a final example for this video. So we have the sum from n equals 1 to infinity of n squared over 2n factorial. So again, we're going to use the exact same process. We're going to find our a sub n, but our a sub n is just going to be the argument. So we have n squared over 2n factorial, which means our a sub n plus 1, this one's a little trickier because what we have here is n plus 1 squared over, now this will turn into 2 times n plus 1 factorial, but that's the same thing as 2n plus 2 factorial, right? Because what we have in here is 2 times n plus 1 factorial, but when we distribute the 2, we get 2n plus 2 factorial, right? So that's all we did there was plug in the n plus 1 for this n, but when we distribute it turns into 2n plus 2 factorial. So let's go ahead and set up our limit. Right now we have everything set up that we need for the ratio test. The limit is n goes to infinity. Absolute value, a sub n plus 1 is all of this, n plus 1 squared, over 2n plus 2 factorial, and all of that's divided by the original a sub n, so n squared over 2n factorial. Okay, and then again we have this nested fraction. We're going to flip and multiply, so when we do, we get the limit as n goes to infinity. When we have one fraction bar now, this will be n plus 1 squared times 2n factorial, right? This will come all the way up to the top, and then these two will combine. So in the bottom, we'll have n squared times 2n plus 2 factorial. Okay? So at this point, what we're going to want to do is try to cancel out the factorials like usual. So we want to examine this 2n plus 2 factorial, right? This is the bigger term, so we're going to have some stuff left at the end. But let's look at what it is. So we have 2n plus 2 factorial. Now that's going to be equal to, so we take 2n plus 2, and we multiply by itself minus 1. So that's going to just be 2n plus 1. And then again, we're going to multiply by this minus 1. But that's just going to be 2n, right? And so then from that point, we keep going down and down and down. That's just 2n factorial. So this is the same thing as 2n factorial, right? That's how it breaks down. So whenever we cancel this, which we will be able to, because we end up getting that 2n factorial term, we're going to have an extra factor of this left over. So what we have here, when we rewrite it, the limit as n goes to infinity, absolute value, so we still have the n plus 1 squared times the 2n factorial, but in the bottom, we're going to have n squared times 2n plus 2 times 2n plus 1 times 2n factorial. Right, so it's a little trickier with this one because of the way that it's set up, but we can still cancel out these 2n factorials, and we just get the limit as n goes to infinity, absolute value. The top is just going to be n plus 1 squared. The bottom is going to be n squared times 2n plus 2 times 2n plus 1. Okay, so we've actually been able to cancel out everything that we needed to, in order to look at how we can actually solve this limit, right? Because the factorials are the hard part. Everything else is polynomial, which we can do using just the degree rule, right? So at this point, let's look at the degree of the numerator and denominator. The degree of the numerator, if we FOILed this out, would end up, the highest degree term we would get is an n squared, right? So we have an n squared right there. Now up down here, we would have n squared, right? So that's already going to cancel all this out, but we still have two more terms. We have a 2n and a 2n, which will be a 4n squared. So what we end up having is a 4n to the fourth down here, right? So that's, of course, that degree is much bigger, which means it grows much faster than the numerator does. So since the degree of the denominator is bigger, we know that this limit will actually go down to infinity, right? Because as the denominator gets bigger, the whole fraction gets smaller. I think I said infinity. It should go down to zero. This limit, because of the degree rule, will go down to zero. So that means that L equals 0, which of course is less than 1. So we can conclude that the sum from n equals 1 to infinity of n squared over 2n factorial, since it's less than 1 by the ratio test, it converges. That series converges. So yeah, I hope this was helpful. I hope that this made sense. This last one was a little bit trickier, but the process is exactly the same. The hard part I think about this one, honestly, is this factorial term that we have. And then this last limit, if you don't remember the degree rule very well from Calculus 1, can be a little bit tricky. I mean, if all else fails, you could FOIL this out and then divide every term by the highest term in the denominator. Right? That's the technical way you can do it. But at this point, we can kind of just compare them. We know this degree is 2, this degree is 4, and since 4 is bigger than 2, the denominator grows faster, which means that everything gets smaller and smaller and smaller. But yeah, so hopefully this was helpful. If you have any questions, feel free to let me know in the comments. But if not, then I will see you in the next video. Thanks for watching.